Hey everybody, I want to talk to you in this video about how to do a hypothesis test. And we are going to start out by talking about what a p-value is. Turns out that's the number that we are going to use to determine which hypothesis we believe. So let me go ahead and go back to the notes and we'll get started right away. So here's the idea. So just to remind you of the basic logic of how hypothesis testing goes, write our hypotheses, get our sample. Then we do this conditional question of if H naught is true. So if the null hypothesis is actually true, then the sample that we just took, we determine if it's really weird, right? It doesn't comport at all with what we would expect. If the null hypothesis was actually true, that causes us to reject the null hypothesis, right? That's how we determine if we think the null hypothesis is true, is if our sample goes with that idea. If it seems to go fine with that idea, then we don't reject the null hypothesis. Remember, null hypothesis is the default, and so we need strong evidence to reject the null hypothesis. And if we get that strong evidence, then we will reject the null hypothesis. Now, here's where we have to talk about some math. So here's the idea. Our definition of really unusual is going to be if our p-value, which we will define in just a second, is smaller than alpha. Alpha is the probability of making a type 1 error. And our p-value, which I will show you in just a second, is basically we just compare that number to alpha. If p-value is smaller than alpha, we reject the null hypothesis. If it's not, then we don't. That's it. Here's the logic. So let me explain what a p-value is, and then I will attempt to explain the logic of why we would do such a thing. So here's the p-value. P-value of a statistic is the probability that we would get such a statistic, or one that is even more unusual, if the null hypothesis is true. So by even more unusual, what I mean is would cause you to reject the null hypothesis even more strongly, if the null hypothesis is true. That is a mouthful. And if you didn't get that on the first time around, you are not only are you not alone, you are in the vast majority of people. I don't think I've ever met anybody who understood p-values right away. So let me try to explain. Here's the idea. P-value is a probability, and it's a conditional probability, right? So it's a probability of it's the likelihood of getting the statistic that we saw if the null hypothesis is true. So it starts with the condition. So given that the null hypothesis is true, the p-value is the probability of getting the statistic that we saw, or one that's more extreme. So let me show you what I mean by that. I think I want to draw a picture here. Yeah, I think I want to try and draw a picture here. I might be getting this a little bit out of order, but I hope not. Okay, so here's the idea. Let's say that this is the sampling distribution of some statistic, or of some mean, right? So this is a bunch of X bars. This is capital X bar. Is this distribution in reality, right? And so the mean of this distribution is there. When we take our sample, we are going to get some X bar, some little X bar. Which is to say, we're going to get something along the X-axis here, and we don't actually know what mu is, right? That's sort of the thing that we're doing with our hypothesis testing and confidence intervals and all that stuff. With statistics in general is attempting to find actual mu. We get some X bar, right? So let's say it's here. X bar. Right, so that's some X bar. When we write our hypotheses, what we're going to have is some statement like this. Null hypothesis, mu equals 10. Right. Let's say our hypotheses look like that. Then what we're going to do is we're going to say, all right, I'm going to start with the assumption that the null hypothesis is true. Remember, that's the given part in our conditional probability, is the null hypothesis being true. So this mu here is actually 10. Now, we don't know that it's actually 10. We're just hypothesizing that it is. So, oops, that's not the right button at all. Pardon me. Sorry, I've opened up a bunch of crazy things. I don't know how much of this shows up on the video, but stuff's happening. All right. So we start with the assumption that the null hypothesis is true. And if that's the case, then this is the graph we would get. So the p-value, let me just pop back there for 1 second so I can point at the definition again. The p-value is the probability that we would get the statistic that we got, or one that's even more unusual, which is to say would cause us to reject the null hypothesis even more if the null hypothesis is true. Well, if the null hypothesis is true, then our sampling distribution looks like this, and the probability that we would get such a statistic, which is to say this one, or one that is even more unusual or even farther away from the mean, is this. So another way of saying what the p-value is if it's actually the case that mu was 10, what's the probability of, and the alternative is greater than, and the alternative hypothesis is that mu is greater than 10. What's the probability of getting the statistic that we got, or one that's even further in the direction indicated by the alternative hypothesis? And it's this area. So this area is our p-value. It's right here, p-value. Which I hope is not too surprising, given that probabilities area, and remember several chapters ago, we talked about that we're going to be using this concept that probability is area all the time. P-value is a probability. It is the area on some distribution. This distribution, by the way, is called the null distribution. It's called that because it is the sampling distribution of the relevant statistic that we would get if it was the case that mu was actually 10. Right? This, by the way, is why we have to start, or is why the equal sign always goes in the null hypothesis, because we need our parameter to equal something if we are going to have a null distribution. Right? If we don't have an equal sign in here, like we just had a mu less than 10, if mu is less than 10, well, that doesn't tell us what we should use for mu. And we need something to use for mu. This also is why it doesn't matter if you use less than or equal to in this case, because we're just seizing on the equal to make the null distribution. Right? So that's why mathematically it really makes no difference which one you choose, whether you write it as less than or equal to or equal to. It does have to be the opposite direction of, or it has to be, contradictory to this. So that's the idea. This is how you calculate a p-value. It's essentially just the area on a graph. And then the way we're going to find that area is by a calculator, probably normal CDF a lot of the time. Other times there are just buttons in there for like, do this hypothesis test, which we'll talk about in a little bit. But all that stuff that we did with finding areas in normal distributions, this is why we did it. is so that we can do hypothesis tests, because that's what you do in a hypothesis test, is you find the area in some distribution. A lot of the time, those distributions are normal. Once we get to chapter 11, I want to say, they stop being normal, at least some of the time. So yeah, for the next couple chapters, our distributions are normal, and the way you find p-values is finding an area in them. The trick is just finding which area, or figuring out which area you want to find. The actual process of finding a p-value is actually very quick, right? You're just going to do a normal CDF in your calculator, which we've done 100 times before, and then that'll do it for you. So this is the basic idea. P-value, again, let me just reiterate the definition. The p-value is the probability that we, p-value of a statistic is the probability that we would get such a statistic, or one that is even more unusual, if the null hypothesis is actually true. So the way we address the conditionality of this, that the null hypothesis is actually true, is we are working on the distribution that is defined by the null hypothesis, right? If mu is actually 10, then our sampling distribution of all possible x bars looks like this. So that's the if null hypothesis is true part. And then the probability part is, well, here is our actual statistic. Given that and our alternative hypothesis, what is the probability that we would get this or something that is even further in the direction of our alternative hypothesis? That's the p-value. And so that's just an area here. Okay. Let me pop back to the notes. So the reason small p-values cause us to want to reject the null hypothesis is the idea is that probability that we just found is essentially how likely it is that we would find such a statistic by random chance if it was actually the case that the null hypothesis was true. That's one way you can think of the null hypothesis, or excuse me, of the p-value. It's the probability that we would see the statistic that we saw by random chance if the null hypothesis is true. If that number is very small, that means that if the null hypothesis was actually true, it is very unlikely that we would see such a statistic, which causes us to think that the null hypothesis is probably not actually true and reject it. And on the other hand, if it's not that unusual, if the number that we get is a relatively large probability, then that would make us think, oh, this is relatively likely to happen if the null hypothesis is actually true. So I don't have evidence to reject the null hypothesis, so I won't. So that's the idea. And our definition of relatively large or relatively small is alpha, probability of a type 1 error. So in general, if the p-value is smaller than alpha, we reject the null hypothesis, because alpha is our cutoff for reasonable probability, essentially. If the p-value is bigger than alpha, we don't reject the null hypothesis. The fact that there's an equal sign in this makes, in practical terms, absolutely no difference whatsoever. That you're never going to get a p-value that's actually equal to alpha. I suppose it's theoretically possible you could, in which case you reject the null hypothesis, but it's never going to happen. So that's what we mean by small or big. Small p-value is p-value smaller than alpha. Big p-value is p-value bigger than alpha. I'm going to make another video. The last page of this worksheet, or these notes, by the way, or the second to last page, is titled, "Why do we compare the p-value to alpha?" Right? Because that is very much the natural question of why are we doing it this way? And I'm just going to say that the answer is complicated. And if you want to see that, I'll put another video up of why we compare the p-value to alpha. It's actually a really interesting topic. But just to avoid the complication of that for right now, I'm just going to just take this at face value. Just believe me that this is what we want to do. And we're going to do a couple practice problems, basically. Okay, so again, I guess the thing I just said is that paragraph there, because that's, if you're a naturally curious person and I tell you, all right, we're going to compare the p-value to alpha, given that those two things are both quite complicated individually, the natural question is, why? Why those two? They don't seem that much alike. They actually are. They're actually very similar to each other. And so comparing them makes perfect sense. And if you want to build on that, see the video on why we compare p-value to alpha. And for right now, let's do some practice problems. All right. FDA is responsible for accurate labeling of food packages, which is true. Allison is an FDA inspector, and she is investigating a complaint that a certain company is underfilling their chip bags, those dastardly profit seekers. The company claims that the bags each contain 3.5 ounces of chips, or I should say, the company claims that the bags on average contain 3.5 ounces of chips. So we want to write hypotheses for Allison to do this hypothesis test, and then we're going to see a result here. All right. So our hypotheses should go something like this. I'm going to go ahead and clear this off. Our hypotheses should go something like this. Null hypothesis, alternative hypothesis. All right, so the null hypothesis is Allison's default, just to say the thing that she thinks, absent other information, right, in case nothing weird happens in the sample, is the thing that she's going to continue to believe. Which is to say, in this case, we should probably give the benefit of the doubt to the company, right? They're being accused of something, accused of cheating, essentially. And we would need to see proof of that to really believe the accusation. In general, we should probably believe, or we should probably just default to the company's probably doing it okay. Just to say that the mean amount of chips in the bag is at least 3.5 ounces. And the alternative, if we see some significant evidence to the contrary, would be that the mean is less than 3.5 ounces. So again, mu is population mean weight of the chip bags, and 3.5 is the number of ounces we are comparing it to. So those are my hypotheses. So I haven't shown you how to actually calculate a p-value. I mean, I guess I did. We could probably figure it out right now, but for right now, we'll do that in a little bit. But for Allison does her test, and here's her p-value, 0.431. At a significance level of 5%, should she reject the null hypothesis? So, two things. One, I have deliberately given this to you in decimal form and this one in percentage form, because I want you to be able to go back and forth between those things very smoothly. And so practice. This 0.431 is 43%, right? So her p-value was 43%, 43.1%. And we want to know at a significance level, which is alpha, should she reject the null hypothesis or not? Well, the p-value here is greater than the significance level. And so that means that no, we should not reject the null hypothesis. P-value is greater than alpha. Don't reject the null hypothesis. Quick tip for you here, a thing that I find helps students a lot and helped me when I was learning this, several years ago. The answer to the question, should I reject the null hypothesis, is the same as the answer to the question, is the p-value smaller than alpha? So I always ask it that way. Is the p-value smaller than alpha? No. So I do not reject the null hypothesis. Right? This is not enough evidence to make Allison think that the company is actually underfilling their chip bags. So I'll write her conclusion real quick, and then we will come right back to this. So Allison's conclusion should be something to the effect of, there's not enough evidence to suggest that the company is underfilling their chip bags. So I'm going to go ahead and write that down. This is a thing that people get very hung up on with the wording of, and if you've had a statistics class before, I know some stats teachers are really picky about this. I'm not. The thing I care about is get the right idea on the paper, right? I don't care if you say we accept the null hypothesis or we fail to reject the null hypothesis. Those are not technically logically the same, but they both capture the right idea, right? So my conclusion, there's not enough evidence That's a weird G. Evidence to suggest the company is underfilling their chip bags. Something like that. In general, you often see something like there is not enough evidence or there is enough evidence, and depending on how you phrase these things, you can work them around to mean either we reject the null hypothesis or we don't reject the null hypothesis. In general, the way you want to write it is not enough evidence means don't reject the null, and enough evidence means do reject the null. Right? We're defaulting to the null, and if there is significant evidence to reject it, then we will reject it. And if there is not significant evidence, significant evidence to reject it, then we won't. Right? So I didn't reject the null hypothesis, so there wasn't enough evidence to reject it, to suggest that the company is underfilling their chip bags. Sorry for my handwriting. It looks bad even by my standards. Anyway, that's the way you want to write a conclusion. So, oh, and by the way, one thing I guess I will mention right here is it's really important that your conclusion have two properties. Three properties. One, get across the right idea, right? Get across the thing that you believe is true based on the data. Two, it should be written in plain English, no jargon. What's the third one I was going to say? I don't remember what the third thing I was going to say was. There was a third one I had in mind. Plain English. Write your conclusion in plain English because it is, I guess I'll give you a little bit of a Spider-Man speech here. As someone who understands statistics, you are in the vast minority in the population. Most people do not. Therefore, it is incumbent upon you to write things in a way that anybody can understand, essentially, without having to know any statistical jargon, right? So one thing that I've seen other stats teachers do that I really disagree with is their conclusions are always something like, we reject the null hypothesis because the p-value is smaller than alpha, or we fail to reject the null hypothesis because the p-value is greater than alpha. I hate those conclusions, despise them. I want because they cannot be read by someone who doesn't understand statistics, right? Someone who hasn't had this whole spiel about what a p-value is, what alpha is, and what it all means, cannot understand what that means. So write your conclusion. Oh, I remember the third thing I was going to say. Write your conclusion in terms of things that were in the problem and in plain English, right? This was a question. The third thing I was going to say was writing in terms of things that were in the problem. This was a question about whether this company was underfilling their chip bags or not. And so your answer to that question should say, yes, they were, or no, they weren't, right? And so the answer to this question should refer to chip bags and the weight in chip bags, or whether they're underfilling or not underfilling their chip bags. We don't have enough evidence to suggest that they were underfilling the chip bags, so that's what we say. I didn't say anything about p-value, didn't say anything about alpha, no jargon. Plain English, anybody could understand this, right? Anybody who was reading about this and casually read the conclusion would know what this conclusion means. There was not enough evidence that they were underfilling the chip bags, so we assume they aren't. There you go. That's your conclusion. So that's how I want you to write your conclusions. And I actually think this is fairly important. As somebody who is conversant with statistics, it is partly your job to interpret those statistics for people who don't understand them, which is going to be almost everybody you know, right, for the rest of your life. Very few of those people will actually know statistical jargon and will not know what a conclusion means unless you put it in plain English and in terms that anybody can understand, and that reference the things in the question that's being asked, right? So do that. Your conclusion should be in plain English, be use the same terms that were in the problem and get across the idea that you were trying to get across in a conclusion, which is to say, what's the answer to this hypothesis test, right? Which one of these hypotheses do we think is right? So when you're writing one, that's what you want to ask yourself. Which one do I believe is right, based on the p-value versus alpha thing? And then say what that means in plain English in terms of the problem. That's how you want to write a conclusion. Oh, and by the way, if you're having trouble doing this, which I almost guarantee you will, basically everybody has trouble doing this when they're starting out. You can have like a halfway point to your conclusion by asking yourself, okay, which hypothesis do I think is right? Right, and so you look at this p-value of 0.431, and you say, okay, significance level is 5%, alpha is 5%, this is 43%, so I think that I am going to not reject the null hypothesis, just to say, I think the null hypothesis is true, right? I'm not rejecting it, so that's the thing that I think is true. And so you look at it and you say, okay, the actual mean is at least 3.5 ounces, right? And if you kind of get halfway to what you believe by saying the mean is at least 3.5 ounces, that really gives you a good head start on writing a good conclusion, right? Well, if the mean's 3.5 ounces, then the chip company's not underfilling their bags, right? So now we don't want to say it as there is not enough, or that the chip company is definitively not underfilling their bags. What we want to say is, standard statistical hedging language, we don't have enough evidence to suggest they're underfilling their bags. They could be, but we didn't see it, right? We don't have enough evidence to suggest that the company is underfilling their chip bags. It's kind of the simplest way you can put this, that you can put this in, and that would be logically correct. Okay, let's do another one. I think I have like 2 or 3 more. Oops, that was not the button I meant to hit. Let's go back to the notes. Oh no, we're just doing one more here. Okay, so I want to do this question next. In the US, it is actually the case that 91.34% of the people who are eligible to vote are actually registered to vote, which sounds great, right? That's over 90%. That's actually not that good, right? That means that something like 8.66% of people who are eligible to vote are not registered, right? So like 1 person in 12. It's not great. Anyway, we would like to see if the fraction in Santa Barbara is the same as the country overall. So we take a sample of 400 citizens who are eligible to vote and find out if they're registered. There was a phrase in there that's really important that I didn't say because it wasn't printed, that you should get used to trying to hear in your mind. We would like to see if the fraction in Santa Barbara is the same as the country overall or not. So we take a sample of 400 citizens, right? The or not was not printed here. I did that deliberately. But that's what you should be hearing in your brain when you see, we want to see if this is the same as that or not. So we're going to take a sample, right? Because the or not tells you that the alternative hypothesis is two-sided, that it's going to be, well, we'll talk about how to calculate those a little bit later, but it tells us that either much higher or much lower, both of those things are going to cause us to want to reject the null hypothesis. So let's see, we'll talk about that a little bit later. That turns out to be that does turn out to be really relevant to us. But for right now, I'm just telling you what the p-value is, right? P-value after we calculate it is 0.0153. So let's write some hypotheses, see what we're going to do with that p-value, and write our conclusion. Clear this off. Okay, so we are checking to see if the proportion of Santa Barbara or eligible Santa Barbara voters who are actually registered is the same as the national proportion. So our null hypothesis is not about mu, it is about P, the proportion of registered voters in Santa Barbara, equals 91.34%. Right? absent other information, we're just going to think that Santa Barbara is probably the same as everywhere else. Alternatively, it might be the case that Santa Barbara is different. We make no claims about whether we have more or less registered voters than you would expect. Just that it's different, right? Could be either direction. So there's our hypotheses. We do the test. We get a p-value of 0.0153. So 1.5%. We got a significance level of 5%, which, by the way, I've been using 5% here because it's standard. Everybody uses 5% all the time. If you ever want to publish something, it's got to be 5%. Basically, I'll have a little bit of a discussion about that maybe in a different video about how arbitrary that is, but it's 100% arbitrary. It's just the number everybody agreed to use and then kept using forever. So if you're trying to publish something, 5% is the thing you want. Most of my questions will be about 5%. Once in a while, I'll throw you a curveball and make it something else, but mostly 5%. All right, so our alpha is 5%. We got a p-value of 1.5%. 0.0153 is 1.53%. And so should we reject the null hypothesis? So without scrolling up to look, I will just say, my question is the p-value smaller than alpha? Yes, it is in this case. So yes, we should reject the null hypothesis. This small p-value makes me want to reject the null hypothesis. So our conclusion is we believe that the alternative hypothesis is true, and we need to get that into words somehow. So my conclusion is that the proportion of eligible Santa Barbara voters who are registered is not 91.34%. If you want to throw in there is enough evidence to suggest that, I'll go ahead and do that. This evidence suggests the evidence. Oops. Oh my gosh, that's so messy. That is the proportion of eligible Santa Barbara voters who are registered is not. I'm going to say 91.34%. It would be 100% fine, and maybe even better, to say something like the proportion of eligible Santa Barbara voters who are actually registered is not the same as the rest of the country, right? Or it's not the same as the national average. That'd be okay too. Either one of those is fine. I don't necessarily think that one is better or worse than the other. They're just kind of different ways of saying the same thing. So there we go. That is my conclusion and the end of my hypothesis test, right? Once you've written your conclusion, there you go. That's your test. So let me make a quick point about just a quick callback to the errors video. Here, we rejected the null hypothesis. There is only one kind of error we could make if we reject the null hypothesis, right? We could make a type 1 or a type 2 error. This would, sorry, I said that really badly. The only error that we could make here would be a type 1 error. We can't make a type 2 error because we did not fail to reject the null hypothesis. That was really awkward. We think the alternative hypothesis is true. We did reject the null. And let me just make a quick trip back to errors here and mention why there's only one that we could make once we've done that. The thing that we think is actually true in this case is the alternative hypothesis, right? So once we think the alternative hypothesis is true, we are not looking at this column anymore. We are only looking at this one. So we think the alternative hypothesis is true. If it is actually true, great, we've made a correct decision. If it is not actually true, then we've made a type 1 error, but that's the only option, right? This is not a thing that we could get because we don't think the null is true. So once you have made a determination about what you think is true, only one of the two errors is possible, right? Before you make the determination, you could theoretically go either way and you could be making either error. But once you have made the determination, then there's only one of the two errors. If you don't reject the null hypothesis, it's possible you could be making a type 2 error. If you do reject the null hypothesis, it is possible you could be making a type 1 error. But again, right now I'm mostly just concerned with getting this down. So notice that the way I've written this talks about voter registration as opposed to what percentage of voters, of eligible voters, are actually registered, right? That was what the question was about. So that's what my conclusion should be about. It is in plain English, plain-ish English, that anybody could theoretically understand. And it gets across the idea that I wanted to convey, which is that we think that the proportion of registered or of eligible voters who are actually registered here is not 91.34%. So those are the things you want to look for. Plain English, references the same things that were in the problem, and gets across the idea that you wanted to get across. I'm not picky about what particular types of language you use or how you say that. Try to get good at making it as smooth as possible, but you don't get marked down for not having the exact right phrasing. There's no magic phrase to get points, right? That's the thing I want to get away from. So with that, I think I want to stop here. The next video is going to be about actually calculating p-values, which is, it's basically just going to be TCDF or normal CDF. Yeah, I don't know if we've used TCDF in this class yet, but it's easy. You'll see in the next video. It'll be normal CDF a big chunk of the time too. Which again was a thing that we were doing back in chapter 7, I believe. So yeah, with that, I think that's all I want to do. I just want to, sorry, fumbling around with my computer here. With that, I think I want to go ahead and end the video. And so the next one will be about actually calculating p-values. And then there'll be another one about why we compare p-values to alpha. There's a very good reason. And it's really not intuitive at all. But I encourage you to go ahead and read the second to last page of the notes and watch my video if you're still curious about why we do that. So I'll go ahead and end the recording now, and I will see you in the next one.